So we've been talking about the Lac Operon, and I want to remind you of the essential structure of that model. We let X stand for the intracellular lactose concentration, and then we write a differential equation that says basically the change in intracellular lactose is produced positively by lactose import and then negatively by degradation. And then to put the math on there, we said that the degradation term, we were going to use a very simple linear R fraction of X is degraded in a unit time. And then for the import term, we used that sigmoidal function. And that sigmoidal function had this form. And then the question was, why this sigmoid? And why did the cell choose that shape of a function? And the answer was clear as soon as we drew the vector field plot. And you'll recall that in the vector field plot, we're going to plot X over here, and we're going to plot over here the two components of X prime, the positive component and the negative component. So the import term is the positive component, and I'm going to draw it like that. And then we said the degradation term, which is just a linear term, is going to look like that. There is the line of slope R. And then we said, ooh, look, how many equilibrium points does this differential equation have? Well, we just solved it graphically. X prime equals 0 when import equals degradation. And just looking at the graph, import equals degradation 1, 2, 3 places. And those give us the 3 equilibrium points now drawn on the X state space. And so the answer, by the way, to the question, why did the cell choose a sigmoid, is notice that if it chose a rectangular curve, for example, let me just draw that here, that you would not then get 3 crossing points, or an exponentially growing curve, or a curve that rises and simply rises and saturates. Only the sigmoid has 3 points of intersection with the straight line, and only the sigmoid will give us the 3 equilibrium points and the biological switch. So that's great. But now I want to discuss a really important issue. And I want to start with a little observation. I drew the blue curve, and I drew the red line. And I said, oh, look, 1, 2, 3 crossing points. And it might have crossed your mind to ask, well, why did you draw that red line? What if you had drawn this red line? After all, how many times does this red line intersect the blue line? And the answer is only once. And if you ask, well, what about way down the road? The answer is the red line is only going straight up, and the blue curve is flattening out. So these two are never going to meet again. That was it right there. There's only a single equilibrium point, and it's at the low value. Then you might have also said, well, wait a minute, what if this is, remember, a steeply sloped curve means R is large. because r is the slope of that curve. So for very high values of r, there is only going to be one equilibrium point. Now, conversely, you might also have said, well, what about very low values of r? There's a very shallow sloped curve that has a low value of r. And how many times is that line going to intersect the blue curve? And the answer is once. It's not on this page. It's going to intersect. This line is going up and up and up, and this curve is flattening out. So these two are going to meet right around there, and that's a very high value of x and a single equilibrium point. Notice there's no intersections here. So the question, how many equilibrium points does this system have? The answer is complicated. The answer is it depends upon r. And that's the subject that we will now immediately address. So the number of equilibrium points depends upon the value of r. And for very low r, we have one equilibrium point at a high value of x. For intermediate values of r, we have 3 equilibrium points. And for high values of r, we have only one equilibrium point at a very low value of x. So this is the first time we've seen this phenomenon. And it's very, very important because this is an example of a qualitative change in the system. And people often talk about math as quantitative, but this is more than just a quantitative change. This is a qualitative change. The system has acquired new equilibrium points or lost them. So we're going to make a new kind of diagram. And the first thing we have to do is give this phenomenon a name. And we're going to give it a name. It's called bifurcation. And this is a word you're going to see a lot. This is a very important word. I'm going to define it a little verbally right now as a qualitative change caused by a quantitative change in a parameter. And we'll define a little bit what I mean by a qualitative change. I mean a change in the number of EPs or a change in the quality of the EPs, that is from stable to unstable or from unstable to stable. So this is a very important general phenomenon. And in order to graph the bifurcations that occur in this system, we're going to make this new kind of graph, and this new kind of graph is called a bifurcation diagram. So in a bifurcation diagram, we're going to make a new kind of plot. And I'm going to do this slowly because I want you to see how I'm making this plot. In a bifurcation diagram, we put on the x-axis a value of the parameter, in this case, r. Now, as you see, for every value of r, we have a different differential equation. And that differential equation may have one equilibrium or 3 equilibria or whatever. Well, I'm going to try to record for each value of r where the equilibrium points are. So let's start with a very large value of r. And as you see, for a large value of r right here, we only have one equilibrium point, and that is at a low value of x. So in other words, the state space for that low value of r is going to look like this. Here's x state space, and here is a single equilibrium point. And recall, blue is positive, red is negative. To the left of the equilibrium point, the blue is greater than the red, so the vector field is positive. To the right of this equilibrium point, the red is greater than the blue, so it's negative, and that's going to continue. So we have one stable equilibrium point at a very low value of x when r is large. So how am I going to represent that? So what I'm going to do is we're going to take this state space with the equilibrium point on it, and we're going to rotate it 90 degrees counterclockwise here, like that. And then we're just going to stick it right here, right at that high value of r. And corresponding to the high value of r, we are going to have one equilibrium point, and that equilibrium point is going to be stable. Now we're going to lower r a little bit. So you can think of, for example, this line. Now what's happening with this line? Well, it's a slightly lower value of r, so we need to put something right there. And you see that it still only has a single equilibrium point. And so the state space is again going to have a single equilibrium point at a slightly higher value of x. So now we're going to put another state space here, and it's going to be a slightly higher value of x, and it's still going to be stable. Now, you see what's coming. As r continues to come down, there's going to be a single point at which it's tangent to that blue curve. And that's a very, very special point. It's called the bifurcation point of the system. And what's happening there is a little mathematically complicated, but remember that's one mathematical point of tangency, because right after that, as we're coming down, we start to get three equilibrium points. And so what has happened after that magic point, which I'm going to put right here, here's the state space. What's happened after that magic point, the low equilibrium point is still there. It's at a slightly higher value. But now we have something new. We suddenly have an appearance of two new equilibrium points. And they are going to be at a moderate value of x and at a high value of x. And we know from our stability analysis that the intermediate value of x, to the left of it, the red is bigger than the blue, so it's negative. To the right of it, the red is bigger than the blue. I'm sorry, the blue is bigger than the red, so it's positive. This is now a new system, and the new system has given birth to I'm going to color the unstable points in red. I'm going to color the stable points in blue. So now we have a new system here with two stable and one unstable. Now what's going to happen as we further decrease r? Well, you see what's going to happen. The high equilibrium is always going to be there, but it's going to be at higher and higher values of x. So now suppose we lower r a little bit further, let's say to this point. Well, we're still going to have 3 equilibrium points. The low equilibrium point, as r is coming down, you see where it intersects the blue curve is at a larger and larger value of x. So this is still coming up, and the pink, the intersection of the red and the blue in the middle, that's coming down as the slope decreases. So this is going to come down a little bit, and this is going to come up a little bit. And then the high equilibrium, where the line crosses there, as that slope comes down, it's going to cross at a higher and higher value. So this stable equilibrium is going to be headed upward. Okay, we continue to drop the line, continue to drop the line, and then there's a second magic point right there, where the curve is, now the curve and the line are tangent at the low part of the curve. And that's another magic bifurcation point. But the important thing is that immediately after that bifurcation point, there is now only the high equilibrium, which is getting higher and higher. And what has happened to these is, well, you see what's happening. As this line comes down, the blue gets higher and higher. The red unstable equilibrium point gets lower and lower until finally at the magic bifurcation point, the blue and the red coincide. And then immediately afterwards, we have only that stable equilibrium point at the high value of x, and that continues as r goes down and down and down. So now let's stare at that for a second, because now what I want to do is I want you to see the shape of the overall diagram. So we've been taking these state spaces, this state space, this state space, this state space, and we've been stringing them out like that, a separate state space for every value of r. And you can think of these state spaces as, if you will, a shish kebab with a skewer and pieces of meat and vegetables. Or you can think of it as a stick with red balls and blue balls, where the red balls represent unstable equilibrium points and the blue balls represent stable equilibrium points. And then we stack up all of these sticks and balls, and then what I want to do is erase the sticks and leave only the balls. And what is that going to produce? It's going to produce a diagram that looks like this. And that is called the bifurcation diagram of the Lac Operon. So now, if we take those sticks and balls diagrams, and there's a stick with balls at every single value of r, and we keep track only of the balls and we throw the sticks away, then we get this S-shaped curve, and that is called the bifurcation diagram of the Lac Operon. There's a name for this bifurcation. All bifurcations have names. This bifurcation has a name. It's a kind of an antiquated name, but the name is so embedded in the literature that you're going to have to learn it, because otherwise you won't be able to understand the literature. It's called a saddle node bifurcation. And I want to explain what that means. So let me just make it clear what we're plotting here. We're plotting the location of the EPs, the equilibrium points. So here's a high equilibrium point, a medium equilibrium point, and a low equilibrium point. What happens in a saddle node bifurcation is a change from a single stable EP goes to a continued stable EP. That stable EP continues. You see, right, and what I want to talk about is what is happening right here at this value of R. As you pass this value of R, the stable equilibrium point continues, but now two new stable a new stable and an unstable equilibrium have appeared. So it's one stable equilibrium point goes to, number one, stable equilibrium point continues. Number two, new pair of an unstable and a stable are born. And so this definition of a saddle node bifurcation is this configuration. A stable EP continues, but a new pair is born consisting of an unstable and a stable, and here's the unstable, and there is the stable. So that is a saddle node bifurcation. Why do they call it a saddle node bifurcation? Because the old word for stable equilibrium point was a node. We even mentioned that when we talked about it. So node equals stable equilibrium point. And this unstable equilibrium point, well, this is one dimension, so we can't even have a saddle. A saddle is a two-dimensional object. But they call it a saddle because a saddle is the generic expression of an unstable equilibrium point in many dimensions. So just live with that. Learn that that's called the saddle node bifurcation. But here is what it is. It's the appearance of a new pair of a stable and an unstable equilibrium. So if you want a nice example to think about what is a saddle node bifurcation, let's go back to our discussion about the hydrological or geological system of the United States. And you remember there is an unstable equilibrium called the continental divide, and that a drop of water to the east of the continental divide flows into the Gulf of Mexico, and a drop of water to the west of the continental divide flows into the Gulf of California. And we said this is a classic case of a stable, unstable, stable equilibrium point structure. And now you can ask the following question. Billions of years ago, there were no Rocky Mountains. And therefore, there was no continental divide, and all water flowed into the Mississippi, single stable equilibrium point. Then, big geological event happens, the upwelling of the Rocky Mountains. And what does the upwelling of the Rocky Mountains do? It produces an unstable equilibrium point there and a new stable equilibrium point there. So the upwelling of the Rocky Mountains is a good example of a saddle node bifurcation. you can, if you want to think about saddle node bifurcation poetically, before the bifurcation, there was only one game in town, the Mississippi River. Post bifurcation, there's a new game. So you may think of this appearance of this new pair of the unstable and the stable is the appearance of a rival equilibrium point. And the sudden appearance of a rival now competing with the old equilibrium point, that is characteristic of saddle node bifurcation. Of course, in the Lac Operon, as we take the different values of R and draw our sticks and balls diagrams, there are, of course, not one saddle node bifurcation happening there. There's two. The first one happens right here. We'll call that R1. And it is the appearance of a new unstable and a stable. And the second one occurs right there. I'll call that R2. And as you pass R2, it's the disappearance of an unstable and a stable. Notice not the same ones. It's the disappearance of these two as they collide with and annihilate each other. So here is a disappearance of an unstable and a stable, the disappearance of the rival equilibrium point. And this is also a saddle node bifurcation. If you call it a saddle node bifurcation, we will not deduct points. Mostly in the literature, this will be referred to as a reverse saddle node bifurcation. The literature sort of reserves the term saddle node bifurcation for the appearance of the two new equilibria. And then the disappearance of these two equilibria is referred to as a reverse saddle node bifurcation.